Welcome everyone to today's Space Syntax Lab seminars. I'm quite excited to have Gözde, Uyar and Åsmund Izaki here, who will present their work on agent simulation framework with spatial choice for multi-level buildings. Gözde has a background in architecture and 10 years of experience working in design research and consultancy in the built environment. She holds an MSc in Space Syntax, Architecture and Cities here from the Basel School of Architecture. Gözde has worked as a senior consultant at Space Syntax Limited from 2014 until 2018, as well as at Superspace, Woods Bagot, Urban Systems, and ERA CO from 2018 until 2022. Besides her long-standing experience working on various scales from building interiors to urban strategies, Gözde has developed an in-depth knowledge and skills of analyzing architectural and urban systems to determine their role in creating human-centric environments. Currently, she's studying at the Royal College of Art in London to explore creative techniques to integrate her spatial analytics background into architectural design projects. Åsmund Izaki has more than 15 years of experience in the field of architectural computation for understanding the behavior and experience of people in space. He has a traditional background in architecture, holding a Masters of Arch from the Norwegian University of Science and Technology. He has co-edited the special issue on empathetic space in architectural design together with Christian Derricks. And currently, he's focused on the research and development of new algorithms and analysis methods at Woods Bagot Design Technology Group, where he, together with the rest of the team, develops innovative agile tools that allow the architectural design teams to interrogate their design decisions in terms of affordance to the user and clients. And together, Gözde and Åsmund have developed an extended simulation framework called Flow to bring an extended response to emerging design challenges in complex buildings and cities. And today we can look forward to hear more about this framework, as well as insights from an applied case study showing the framework in action. And before I hand over to Gözde, I should emphasize we will have a Q&A after the presentation. So if you have any questions, please put them in the chat so we can collect them and answer them at the very end. And with this, I would like to hand over to you, Gözde.
Yes, so we decided to go with my part first because it sort of sets the stage, introduces the overall framework. So that's the sort of direction, the order that we went with. So we both worked on both papers, so it's a really fluid collaboration, I could say. So just starting with the agenda. So we will talk about, a little bit who are we in terms of, who are we in terms of the companies that we have been working, we are working in, and developing these tools and these projects that you will see today. We will then introduce the framework, go through 2 case studies. The first one is a shopping mall in Europe, and then from there, Gözde will take it over, and she will show the airport terminal in North America, and also do the sort of combined conclusions. And this will just be very briefly. So the work that we're showing today is done at ERA, which is a sort of global collective of a wide range of type of people, but it's working as in a sort of consultancy, on a consultancy basis. And on the other hand, we have Woods Bagot, which is the global architecture studio. Okay, so why do we work with agent simulation to start with? And that's because we think it's a really good way to help develop buildings that operate effectively, in order to be able to test this and test how they're used over time. We think agent simulation is a really good tool and a really unique tool for doing it. And it's not really our goal to just test the design and say that it's good enough or it works. It's really in order to test design intention, so that if there's a sort of discrepancy between how the architects think that a building should work and how our system sort of if that gives a different result, that's maybe when something interesting is happening, because you have to say, okay, is some of our assumptions going into the model or the simulation wrong or not valid, or is it something about the way that the architects have imagined or their stakeholders have imagined this to work? And then it becomes really a design tool rather than a sort of validation exercise. With that said, we also want to make sure that we have a comfortable user experience. It's not too crowded. And a really important point is also that we really think, as much as possible, buildings should provide like natural wayfinding and not rely too much on signage. And then what already exists in space syntax to do the agent modeling? So we have from 2001, as you all know, the space syntax-based agents by Penn and Turner. And these agents explore the space freely. You determine, where they enter into the environment, and then they move around. And that works really well for weak program buildings and environments. And then in 2012, we have the paper from Ferguson, Friedrich, and Karimi that introduced the origin destination weighted agents. In that case, you have both an origin and a destination, where you have the agents moving between. And this works really well for strong program buildings and environments, where you sort of naturally know, okay, where the agent's coming from, where they're going, and you can reason about it. And we actually use this method as it is for determining the movement paths for each of the agents, but it's integrated in our framework as one of the steps. And as you may have noticed in the title, we have it's called the Agent Simulation Framework with Spatial Choice. And how we use spatial choice is using this definition from Tommy Yaling. So it basically indicates a preference for one spatial location over another, and where physical distance is only one of several attributes which may determine the choice. Travel time, ease of wayfinding, or scenic quality of the route are examples of other attributes. So it's basically a way to define, if you have a choice between going between multiple spatial locations that offer the same program, let's say, what are the attributes that determine, how can you evaluate which ones are more attractive in a way? And that's really the principle for our framework in order to model the full sort of the full choice of the agents. So what does flow really do then? So instead of basing it on the origin destination matrices, we simulate user journeys as an outcome, and it can incorporate schedules and timetables. It can incorporate a lot of different data sets. So far we've been working very specifically with the data sets that are sort of available for each project. An important point is that we also simulate the movement across floors, right? So movement across stairs, escalators, and lifts. And with this approach, we're also able to create animations that show sort of persistence across, across stairs, across different visits to with dwell times to do different activities. While, there are some new things, we also thought it was really important that it should be compatible with the space syntax workflows, the deliverables, because these are really useful, and there's a tradition and a knowledge around how we can interpret and use those outputs. And we were also very specific that we wanted to not only consider the metric distance, but take in as much as possible in the framework. And then for specific projects, we can use what is relevant in relation to the user type in that building. This is just showing the overall simulation framework, which is based on different steps. And the next few slides is going to just show each of those steps, quite briefly, but describe what they are. So it consists of constructing our own sort of spatial representation of a building. We then generate the population for a specific scenario. We determine the itinerary for that population of agents, what they're in general doing. Then we are using, as we mentioned, the origin destination weighted agent method for the movement paths. And finally, that produces like a data set for the simulation that we use, that we then construct the maps and animations from. So the first part is basically constructing this representation of the building, which is a bit of a larger project for us, but we use it for all kinds of spatial analysis, but also for these simulations. And we have developed a sort of bespoke schema in order to represent the multi-level buildings in a sort of topological way, where you have the walkable or the circulation areas and how they're connected with escalators, and how sort of secondary program is attached to this, in this case, shopping units with frontages and entrances. And we then have like a code base to produce a lot of spatial analysis metrics on this model, which drives the agents, but they can also be used by themselves as a sort of spatial analysis outputs. Then we build population. How we represent the users are a bit different for different for different sectors, for different typologies. But the important thing is that the user has certain tasks or certain activities they want to do. They can have dwell times, they can be have a specific order, and they can be mapped to a specific destination, or they can be a type of program that is available in several places. And other, basically any attributes that is affecting their decision tree. This is going a bit back to the spatial choice, which we use for determining the itineraries. So we have the agents, they want to do certain activities. And when they do have the choice between multiple destinations, this is our sort of mathematical, like translating the spatial choice definition by Yerling into mathematical formulas. But it's basically allows you to give a score for each. So if you have multiple candidates, you give each a score, and depending on the user type, that might include the metric distance. It usually includes the angular distance and the visibility, and the capacity at that destination. It's more of a scaling factor to these other components, and it's really not that complicated as it might look. You look at the formulas. It's basically looking at, how far away is that unit in relation to a threshold. So if just for take an example, the metric distance, if you say that any unit within 100 meters, we think it's a reasonable choice. So we could have a cutoff at 100 meters. It has a positive contribution to this attractiveness of that destination, and then it just divides it by the other candidates' scores. So you have always a relative performance to say, is it by half the distance? Yes. And then it's relative to the other options. And the second one is basically looking at, if you do have a destination, as we will see in Gözde's presentation later, where at the airport you're going to the gate, for example. What about secondary or intermediate destinations on the way? So it's exactly the same, but looking at how much of a detour, or how much does that add to the distance in this case. And when we have evaluated each of the candidates, it's given a score, and then we borrow this method from Holland, which was originally used for genetic algorithms, where you need to pick, not the very fittest, but like high performers in the population. So it's kind of like a roulette wheel that has different area so the candidates that have a high score has a higher area, and is a higher, proportionally higher chance to be selected, which means that even a destination that is performing less will be chosen fewer times, but it would never be chosen. Okay. So this is all in order to produce this kind of maps, right? And that's where the interpretation and the sort of where it becomes interesting in the design process. So these are probably quite familiar looking if you have done any agent-based modeling. So we have the density of people, like how many people are in each of those cells or grid cells. And then we have the paths, gate counts, comfort levels, and level of service. And I will quickly just show the airport project, which had 3 levels. And the ground level, you can walk also between all the buildings outdoor. And in what we're going to show now, the client asked us, consider a winter scenario, so it's less comfortable to walk outdoors. So in that case, we actually added one more criteria, which was the discomfort of moving outdoors. And you see there's these 3 buildings, and that they're connected on the R1 level, 2 of them, and the third one is connected on the R+2 level. And you can also see the escalators and lifts and some open retail and so on. And we always, there is usually some date sets, but there are also some assumptions that we have to agree with the client and some information that we receive from the client. So we receive, for example, the modal split, how many are coming with the car. So they're coming from below, from the parking garage, and some are coming by bus and some by foot. And yeah, just the scenario we decide, guys actually decided the scenario, which is 3 to 4. This is just to emphasize that we are not always using all the different possible, metrics that went into the formula that I showed before. In the shopping mall, we thought it, the size of the shops, determining the sort of capacity. We use both the metric and the angular distance and the visibility. So frontage visibility for the units, and just the general visibility for the escalators and so on. Plus, we added the outdoor, if it's accessible, through an indoor path, that gave a higher score due to the climate situation. These are the results. So we saw that there was a very high density between the lift and the escalators in one of the buildings. And this could cause some congestion there. On the other hand, we saw there were some open retail units that would benefit from the high movement footfall in one place, and in another place, we thought it would actually be a bit disruptive with the high density, as you can see in the middle. These are the path maps. So again, we can see, the high flow, the open retail, and the sort of a bit sensitive area on the left. One thing that we did realize when we worked with this was that the orientation of the escalators were really essential. Also because they really, we're calculating the angular distances through the escalators across the floors. So actually turning the escalators can really change the angular distances when you move across the floors. Also the visibility, because we're looking at the visibility of the entrance of the escalators. So that we saw as almost like a tool to sculpt the movement. This is showing just the gate counts. We can show the direction of the different gate counts. It's a bit of a question whether this was more useful for us than maybe to show to the client, because it was almost too much information for them. And something like this was much easier for the client to really understand, where is it, no problem, good comfort levels, where would we might have some issues. So Gözde recommended to enlarge the width of one of the lobbies from the lift lobbies. Yeah, and this is basically talking about the same. So we saw it both with the through-in, which is the showing how many people are moving per meter per minute, but also in terms of waiting, how many people have to wait in that lift lobby, both to sort of raise that location. So yeah, so I think that sort of sums up my part, and then handing over to Gözde.
Great. So this is the second paper we presented earlier this year in Bergen. And so I worked on this paper with Åsmund and Freyan. I think she's also on the call, and Richard from Uzbekistan. And so after the shopping mall project that Åsmund presented, we were commissioned by LAVA, the Los Angeles World Airports, to look at the terminal building that they wanted to extend. And so adding on to that previous algorithm and the tool that Åsmund coded, sorry, go back. We needed to add some more functions and some more parameters, because an airport building is much more strongly programmed than a shopping mall. So you have the constraint of the time. You have only a limited time in there until you go to your gate and take your plane. But also the movement behavior is very different. It's linear. So there are areas that are restricted. You can't go back after you pass a certain checkpoint. So it requires a bit more different kind of thinking about the simulating the movement in this building. So also to mention, there are different kind of passenger types. So some of them are like arriving to this terminal, some of them are departing, some of them are connecting, but there's also the leisure and the business passengers. They also might behave differently. So we wanted to take all of this into account, and it was extended. The framework was extended to respond to that. And this is the project site in the LAX airport. So they wanted to extend one of the terminals, and which was two-story terminal, and they wanted it to accommodate 8 gates for domestic flights, some retail units, like some terraces for view to the outside, and circulation spaces. So we were commissioned on that as ERA to kind of run this flow model, but we did some other analysis on this building as well. We knew the envelope of the terminal extension, so we knew where the exterior walls were, but inside was empty. So we helped the Uzbekistan design team to kind of understand where would be the critical points for the retail units, and in terms of visibility analysis and some spatial analysis. But flow was very useful in the case where we wanted to look at specific passenger movement. And the intent was to maximize their experience with increasing wayfinding and legibility of the gates. and also to identify any potential areas for congestion, and also the best locations for retail units. We also looked at the level of service on key locations. So before going into methodology, I also want to say that we only looked at the part in the terminal after you go through the security. So we didn't model anything that was like when you enter the building, you go through luggage drop off, and then maybe you go to a shop there and then go to security. So we only modeled after people pass through security, and then they face new shops or new areas for sitting or eating. So this we had a bit more complex methodology compared to the shopping mall, where the movement is a bit more exploratory, but here it's a bit more coded. So we have this in 3 categories, and so we created a passenger profile, different passenger profiles, and each of them had a different itinerary, and they had different turn-up times and the different activities and the duration they spent on each activity. So not every passenger were departing from the gate, but some of them were landing, and some of them were just changing flights, changing gates within the same terminal. So we had all these 3 main categories of passenger, but we also had leisure and business, but we also had a separation sub-profiles inside them, which I will show in a minute. Then that attractiveness score that Åsmund mentioned also, like in terms of which units the passengers choose, if there are lots of like beverage units, which one do you go to? So we were kind of looking at these 4 things: the capacity or the area of the unit, and the visibility of the frontage. So how much an agent can see while walking in the space. So it's not a general visibility across the floor, but it's from the point of view of the agent, and the proximity to their destination points, but also the shorter detour to destination. So let's say if their end goal is to go to gate A, then they are gonna maybe go to a restaurant that is not too far from it. That was like maybe one of the attractiveness score that could increase the potential for that unit to be selected. And then the circulation was chosen again based on the itinerary and general visibility and the directness. So we used a lot of data to input, so it wasn't all assumptions. So we had some data from the client, but also we looked at some survey results that was done in the same airports a few years ago, and also a similar airport in San Francisco. So with this data, we were able to make the basic, like the initial assumptions of the scenario, set the scenario, which time of the day we are simulating and which hour. So we always want to simulate like the peak scenario. So we know that if it works for the busiest time, then the movement will be okay for the rest of the time in a day. So it's a domestic airport terminal with 8 gates. We know the aircraft's size, so we could find how many passengers per plane, and we assume 90% load factor. We found out in the survey that of the whole year that Fridays were usually the busiest times, and between 7 and 10 p.m. So we wanted to simulate these 3 hours. So we had also done some research about how long does a passenger stay in the airport. So it's up to like 3 hours usually. And then we assign different walking speeds to the passengers, so not everyone walks the same speed. So you can see the rest of the assumptions and data set we used here with like vertical connections and how they reached this terminal. So they had 2 access methods. was won by shuttle bus or by foot tunnel. So we assumed an equal distribution in that. This is the study area. I'm not sure if you can see like the whole screen. But yeah, so the passengers arrived to this terminal building, which was like this floor where we studied. So they can use the escalators, lifts, or the stairs to come up here. And then they have the option to go to, this is after they pass security. So they have the option to go to restaurants in green and also shops. And then toilets in orange and viewing terraces, like some panoramic terraces they wanted to create for people to rest. So there were 3 in this floor. And the gate locations are here. So these are the profiles we created. So we use these percentages and numbers from the survey results done for LAX and San Francisco. We had 4 sub-profiles within each leisure and business passengers, and they had different distribution, but also different type of activity. So some of them went to shopping units twice, whereas the business went to once. And then they also spent a certain time within each, like 10 minutes in a shop, maybe for browsing, and then up to 35 minutes in a restaurant, 5 minutes in toilet. So we kind of input this information before we run the simulation. So time was a very important factor, and we were able to simulate that, and which is also the case for the flights. They all have a certain time they arrive to the airports, and then they depart. So you can see the gate locations on the plan, and we created this. So this terminal doesn't exist. None of these flights exist, but we also created this flight plan using previous LAX flights. So we went through all this data set of the flights arrival and departure times, and we were able to create this time, like the time plan for them. So we calculated the numbers within 7 and 10 p.m., 3 hours, but we simulated both 2 hours and before and after of our simulation period, so that once we start the simulation, we had the numbers already distributed with the logic, with the operation in control. Yeah, so this is showing like how each passenger had a different itinerary. And then we ran the simulation. So around 9,000 passengers were simulated. And this is the kind of a screenshot of the table that that this tool created. So each passenger has an ID, and then there's a column whether they are like connecting passengers or they arrived to the terminal by a plane, and then which flight they took, whether they are leisure or business passengers. They choose tunnel or bus to access here, and like also whether they take escalators or stairs, whether they are female or male. It's quite detailed, and that was like allowing us to identify which toilets they go, for example. So we were able to simulate all that. And this is an output of the journey summary. So this is usually in the space syntax, like the depth map agents, the user puts in this matrix, like you know exactly how many people are expected in that destination. But with this framework, this is an output. So the algorithm and all these parameters that you set actually gives you how many people are at the end in these destinations. So you can like see the distribution of the passengers and their choices of places they go to, and then their gates, or if they are departing the terminal, which way they used to depart. So, and just to show you quickly the results, and this is the flow density, which you have also seen in the shopping mall presentation. Here we can see the overlap of the flow and the key desire line. And then you can see like we had some a bit issues in these corners that were highlighted as very high movement density because there wasn't visibility across. So this kind of part of the terminal could be critical to replan. And we see that towards the end of the terminal, there is less movement overlap, which is an expected result because you don't have as many users. It's the dead end, basically. With this parts, we could then isolate different passenger groups to see observe their movement a bit separately. Because it's a bidirectional movement, there are people in red are leaving these gates to go back, like go towards the exit, whereas in blue, they are approaching this gate. So there's this bidirectional flow happening with maybe minimum visibility here, which could cause problems. We also zoom into some areas to comment about furniture settings. And this was showing the peak 5 minutes on the flow numbers, like how many people are on these locations during the peak 5 minutes. And this was for us to then look at the level of service. So with the Fruin standards, like all these locations were perfectly comfortable. We also wanted to challenge it, and we used Transport for London standards because this is a bit more restrictive. And so we identified one spot that might be a bit problematic, that was a bit more uncomfortable. We suggested to increase the width. The other thing was the client was interested in the performance of retail and the restaurants, and they asked us if we could somehow like give them an annual prediction or rank them. And so this was a kind of limitation for us. We couldn't do that because this simulation was only done for this peak 3 hour. It couldn't be extrapolated to the whole year. So that was maybe the limitation of the tool. But what we did at the end was we grouped these units based on their functions. And then we looked at the average number in each destination, how many people visited them overall during the 3 hour. And we told like whether it was below or above the average. One thing was interesting here was that the terrace, the viewing terrace, like where people can go and look at outside, like the end of the terminal where we see less movement. Actually, this terrace was the most used among the 2 other places. So that's an insight that we wouldn't be able to get with other kind of metrics than flow. So this is just a summary of like what we delivered in terms of recommendations and identifying areas with problems in terms of movement. And just to kind of end with the last 2 slides. Compared to space syntax agents, with this framework, we could simulate complex user journeys across levels. And that also gave us flexibility to account for timing and the duration of activities. So initially it takes a bit longer to set up because that's a bespoke framework that was created for this project. But once we have it like done properly, then it can be replicated to other aviation projects, and it becomes very quick to run. And you can also repeat the scenarios and compare options with very short time. Compared to Legion and Mass Motion, like other pedestrian simulations, the framework doesn't account for waiting times for a destination. Like if a destination is full, then like there is no waiting time that is that we take into account for. Like the crowding, queuing behavior is not captured, but then that makes it quicker to run because it needs less computation time. And in terms of the conclusions for both papers, that with this modular and flexible architecture of the framework, we can develop tools that are sector specific. Like, as I said, with this case study, then we could have this tool applied to other airport projects or other strongly programmed buildings like hospitals or like other places that might require some time, like train stations. And then, so we were able to help this iterative design work, like with the client, there was and the designers, we had, so it enabled this communication between the design and the client. And we still need to do observational, like we need to collect observational data and validate our whole process. So it's overall enable us to look at the complex movement behavior and include time factor to this, which was not accounted for in the other, like the simulation frameworks. And so the input to the to this software is less assumption based than the origin destination matrix in using depth map. So we don't need to put a predefined origin destination matrix. It's something that is created with this tool. That's maybe a benefit. So yeah, I think I'm okay with time. I'm gonna end here.